Welcome back, and this is the last in the series of videos looking at the aromatic functional group. In this video we're going to be concentrating on phenol, so that's a C6H5OH molecule. It has similar reactions to both alcohols and to carboxylic acids, but it should be treated as a unique functional group. The phenols are a series of compounds where we have an OH group directly attached to a benzene ring. So the structure is my benzene ring where one of the hydrogens has been replaced by an OH group. So it's C6H5OH. They're pale pink crystals and they have this strong antiseptic smell. The reason for that is it's better known as carbolic acid. Carbolic acid was one of the first antiseptics ever used, and that's why it has a strong antiseptic smell. It's not used nowadays because it's also quite corrosive and does cause cancer. So we're going to do a series of experiments looking at the reactions of the phenol. You don't need to know all of them, and I will star the ones that you need to be aware of. So the first reaction, looking at how phenolic compounds react as acids. It can react with sodium and you see an effervescence. You're going to break the OH bond. You don't get as much effervescence as you would do with ethanol, and you certainly don't get as much effervescence as you would get with water, indicating that phenolic compounds are much stronger acids. Phenol can also react with sodium hydroxide. Unlike most compounds with OH groups, phenol is actually classified as a very weak acid. So it can actually react with my sodium hydroxide. So if I take my phenol group, just like any other acid, it will lose the hydrogen, this time of this OH group, to make water, and leaving behind the O negative Na positive. Now, phenol is not particularly soluble in water. The reason for this is it has this very large benzene ring which is very hydrophobic. The benzene ring is very non-polar. The OH group at the top can do a small amount of hydrogen bonding, but the lone pair on the oxygen, if you remember from the last video, is being withdrawn into the ring. So that's going to make that lone pair on that oxygen much less available. So you can't exactly have your cake and eat it. If the lone pair has gone into the ring to make the ring more reactive, it must have made the lone pair on the oxygen less reactive or less available. And that explains why it's not particularly soluble in water. So although it's classed as an acid, if you were to add carbonate solution, you would not see any effervescence. And the reason for this is, even though it is a weak acid, it's such a weak acid that it can't actually release carbon dioxide from a carbonate solution, unlike things like ethanoic acid, which can. You can react it with an organic acid to make an ester, but it is quite difficult to do this. Again, this is because of the lone pair on the oxygen forming part of that delocalized bonding system, so it's less likely to react. If you use a stronger reagent, such as ethanol chloride, that's a much better way of getting this esterification reaction to occur, because the ethanol chloride, the C double bond O Cl group, the carbon is going to be very delta positive because it's got two electron withdrawing groups and is therefore much more able to attack the lone pair on the phenol. It needs to be shaken with sodium hydroxide before adding the ethanol chloride, just to basically make it soluble. So I can take my sodium phenoate, I can take my acyl or acid chloride, and I can make an ester, in this case phenyl ethanoates. This time I'm going to get sodium chloride as my product. Instead of using ethanol chloride, I could go one step up and I could use something that's even stronger. I could use ethanoic anhydride to do the same reaction and make the same ester. So if we look at the properties of the benzene ring itself, when it's got the OH group on it, in other words when it's a phenol, if you set fire to it, again you see the typical smoky flame. When you compare that with ethanol or ethanoic acid, there's a much more soot produced. Ethanol burns with a very, very clean flame, as does ethanoic acid. So the hydroxyl group makes the flame become a little bit cleaner, but certainly not as clean as you would expect with ethanol or ethanoic acid. Now, one of the key reactions is the reaction with bromine. So when we react our phenol with our bromine water, we get a typical substitution reaction, and it occurs very readily. What we will see is two things. Firstly, we will see the bromine water decolorizing, so this will decolorize, and you will make a white precipitate. Now the white precipitate you've made is 2,4,6-tribromophenol. You can't stop it doing only one substitute, it will always do 3. And the reason it always does 3 is because the ring is much more reactive to an electrophile now. So you don't need to use bromine liquid and a catalyst. It will work with bromine water. So the bromine is acting as my electrophile in this case, and I get this product. Now this is one you need to know and to be able to balance. So again, we can react it with nitric acid to make a nitrated product, but again you should notice we don't require the concentrated sulfuric acid catalyst, and we use 2 molar nitric acid, which is basically bench strength. And you will see a coloured product being produced pretty much immediately, and you don't need to need the catalyst. But again, it is still electrophilic substitution. So phenols are less soluble in water than alcohols because they've got that hydrophobic benzene ring attached to them, and the lone pair on the oxygen is less available to form hydrogen bonds. They're actually acidic because they can lose that hydrogen off of the OH group to become O negative. The reason they can do that is because that negative is delocalized over the ring, making it less likely for the hydrogen ion to join back. They react in a similar way to alcohols in that they can both react with sodium and they can both react to form esters. However, phenol needs a more reactive reagent such as an acid, or sometimes we call them acyl chloride, or the ethanoic anhydride. The evidence that the OH group is ring activating comes from the bromination and the nitration. Both of those will occur without a catalyst and will occur under milder conditions. So we only need bromine water and we only need bench strength or 2 molar nitric acid. How would we distinguish the phenol from other organic compounds is the fact that they will both decolorize bromine water and produce a white precipitate, and that's a test for a phenol group. There's one last thing we need to know about these substitutes and their effect on the benzene ring. If you have a group which activates the benzene ring, it tends to put further substitutes into the 2 and the 4 positions. So for example, if we have methyl benzene, well, methyl group on my benzene ring is ring activating. This is one of the reasons why I have to control the temperature, because this ring activating will put further substitutes into the 2 and the 4 position. So we get 2, but we can also get 2,4 or even 2,4,6. So if we let the temperature get too hot, so heat above or greater than 55 degrees Celsius, we can get multiple nitrations. So we've got CH3 group, and then we have in the 2 and the 4 positions, and this group here, you can think of this as a substitute again onto the 2 position. And we have 2,4,6 trinitromethylbenzene. Well, the old-fashioned name for methylbenzene was toluene, so what we've made is 2,4,6 trinitrotoluene. It's more commonly known as TNT. It's one of the reasons why you really need to control your temperature when you do this nitration reaction. On the other hand, groups which are electron withdrawing, deactivating the ring, tend to add substitutes into the 3 and the 5 position. So if we're starting just with nitrobenzene, which is ring deactivating, and we add a few more nitro groups onto it, tends to substitute into the 3 position, and obviously the mirror would be on the other side because that is still in position number 3. So last but not least, we need to do this little spider diagram. So sodium metal, or more usually sodium hydroxide, will make the salt. That's going to make it much more soluble in water because you now got an ionic bond on the top rather than a covalently bonded OH group. The test for phenol is this reaction here to make 2,4,6-tribromophenol and also 3 hydrogen bromide molecules. And you've got to remember that this species here is a white precipitate, and you're going to see your bromine water decolorize. We can esterify it. We need to use something like ethanol chloride or ethanoic anhydride. A normal carboxylic acid is probably not going to be reactive enough to get this to work. And again, we can make our ester linkage. And here is my ester functional group. I can use dilute nitric acid, so 2 molar nitric acid at room temperature. I'll probably get a mixture of products, some where I've got 2 nitrobenzene and some where I've got 4 nitrobenzene. If I raise the temperature a little bit, I'm likely to get those di and tri substituted products. So last but not least, we're looking at this large spider diagram on page 24. So with concentrated sulfuric and nitric acids, we make our nitrobenzene. We need to be careful of our temperature, otherwise we're going to get multiple nitrations. We can do our Friedel-Crafts reaction with aluminium chloride as our halogen carrier. There are a few little ones which you might like to be aware of, but that are not technically on your specification, in which case if you boil up your benzene with UV light and chlorine gas, you can get the free radical substitution mechanisms to occur. But those, as I said, are ones which are no longer on your specification, but they're just useful to have a look at. More usefully is the halogenation of the benzene ring by adding my halogen carrier and the appropriate halogen. Once we've got the groups on our rings, we can do all the similar reactions that we would expect. So, for example, here I've made this methyl ketone group. I can now ignore the benzene ring, and this will react just in the way you would expect any methyl ketone to react. In other words, it will react with iodine and sodium hydroxide in the iodoform reaction. It would react with 2,4-DMPH and so on. Same way with these groups. Now that I've got this CH3 group on here, it will act in exactly the same way as you would expect any alkane to react. So for example, chlorine in UV light, it will react to form or to replace the hydrogens on the CH3 group with chlorines. It's much more likely to do that than it is to attack that ring. You'd have to boil it up for quite a while to get that ring to react. Concentrated nitric and concentrated sulfuric, less heat needed, and you'll get multiple nitrations. In fact, if you just added dilute nitric acid, you could probably get at least one of the hydrogens to replace with an NO2 group. So that finishes this series of videos looking at the aromatic functional group. It's one of the key functional groups in organic chemistry, and in the exam it comes up with frightening regularity. So do make sure you know all the reactions, especially the mechanisms, why things like phenol are more reactive than benzene, and why benzene is much more stable than you would expect it to be. Have a go at the questions at the back of the pack, and when you're ready, hand it in, we'll mark it and give you some feedback on it. So until next time, take care, stay safe, bye bye.